So just let me know if you're able to see my screen.
It
So
is
it's
visible.
Powertrain Selection. It's the uh,
Mm.
right. So the whiteboard is what you see now. Hope it's fine. Um, Suchi, can you by any chance just like pin the presentation so that I know that I'm sharing the same still? Is that an option? Okay, I think okay, I can see it. Okay, I think that's great then. Okay, super. So thanks a lot for that. So I'm Sajeeth, and I am what you would probably call as a systems engineer. So I'll tell you what systems engineering, probably spend a couple of minutes talking about that as well. And I'll also probably like tell you a couple of interesting things about what systems engineering, why should we should do that, among other things, right? So we'll start from there. And my agenda for today is to kind of paint whatever you've learned in the last sessions, whatever you know so far. I'm assuming that that is basically something which comes from a academic point of view, and I'm gonna try and kind of like move you towards how the same concepts might work in OEMs, right? So to be more specific, the agenda that I'm gonna be talking about in this session, though it is supposed to be about powertrain, I'm gonna take a little bit of a leeway, and though I will be talking about powertrain and then batteries tomorrow, what I'm going to be more focused on is three different areas. So the first one is about requirements, right? So what is requirements? Why am I, probably even talking about requirements? Is this not something which is extremely easy for people to understand? Why do we basically do that, right? So that's the first thing. Second thing is with respect to how these requirements work, most of the time people understand that a requirement is written in stone. It is not actually, right? So we'll do that. And the third one is how do we detect how the problem, how the product might fail, how a software might fail, and how do we mitigate it, right? So this is basically what we are trying to be tackling today. So I would obviously be very happy if you could participate and probably like interact and kind of make it a little interactive. I understand 6 to 8 is not exactly the right time for a lot, but if you could still like interact would make things a lot more easier for me than just talking about it, right? So that said and done, I'm just gonna just put up a whiteboard here. Let's probably start from here at this point, right? So I said I'm gonna be talking. I'm gonna primarily be talking about something called as systems engineering, right? So I will probably start at this point. Been a little while since I started writing on it, right? So I'm in between vacations right now, so I'm kind of losing touch. So it's gonna be kind of like a little all over the place, but hope you can understand what I've written there. It says systems engineering, right? So the first question is, what exactly is this, right? So I would probably say that systems engineering, I mean, it is a branch of engineering, right? It's kind of something which people do study to be. There are certifications in this. There are organizations like you have IEEE for electronics, you have INCOSE for systems engineering, right? So this is a branch of engineering. It is also an ISO standard. In fact, it is ISO 15288, right? But I believe this is not something which a lot of us have heard about, right? Not many people would be aware of it. Not many people do even understand what systems engineering is, right? And it is my sincere belief that everyone should probably pursue systems engineering as a part of their master's program, right? Or you actually master in systems engineering. Systems engineering is not something which a fresher can do. You'll need to have a lot of domain knowledge across multiple different systems before you can do systems engineering. So my agenda is to start here. I'm going to tell you what exactly systems engineering is, and why should we need to look into it. Okay. And to do this, I'm gonna start giving you some examples, right? So there is a car. It was not launched in India. It's a while back. I think this was in the early 80s, right? The car was called as a Ford Pinto, right? And This car had a very peculiar aspect to it, right? Whether knowingly or unknowingly, right? What ended up happening was they had placed the fuel tank towards the rear of the car. Don't ask me where is the fuel tank even now. Of course, even now it is in the rear of the car, but it's not exactly at the rear. It is a little bit towards the the rear axle, or most of the times it is partially like ahead of the rear axle as well, which means it is not the rearmost component in a vehicle, right? But this Ford Pinto, unfortunately, they put the fuel tank in the rear. And as a consequence of it, you know what might happen, right? The Ford Pinto, whenever there was a crash, right, the car would catch fire. Now, when something like this happens, you would assume that Ford, being Ford, would probably like immediately try to fix this, right? But as the case was, Ford decided not to fix it. Because what they found was that the amount of money it would take for them to fix this problem, right? This was much higher than all the court cases and settlements which they had to endure. You wouldn't believe it, they actually did it, right? This was in the US. They actually did do a study and they found out that it was much cheaper for them to tackle the cases in the court. The judge would slap a fine, they would give a compensation. It was much more easier for them to do that rather than go back and fix the car, right? So now this might, get you thinking, what is this thing whole about, right? I mean, why am I talking about some kind of a failure, and what am I talking about in systems engineering? We were kind of like starting off with something different, and why am I talking about it here? Now, let me try to put a slightly different spin to it, right? Let me talk about something which might hit very close to home, right? Let's kind of like talk about it. Again, a very big disclaimer. I'm just going out on a limb. I'm just thinking about what might have happened. This by no means could be the truth. There could be a lot of other things. This is my disclaimer, right? So let's speak about Ola Electric. Right. Let's speak more specifically about the S1 scooter. Not that they have any other product on the market, but let's speak about the S1 scooter. So can you kind of like hazard a guess, and can you let me know what exactly went wrong with the Ola S1 scooter? Or if you understand what problems happened with the Ola S1, could you let me know what exactly were the problems which were happening with the Ola? The scooter, right? To kind of put it into perspective, this was a company which boasted, if I remember right, somewhere about 55 to 60 percentage market share, right? Again, percentage numbers are some things which can be used to, um, you know, tell a wrong story. If only 1,000 vehicles were sold, and if I sold 600 vehicles, I have a 60% market share. And in 2 years' time, now 10,000 vehicles sell, and I sell only 1,000 vehicles, and I have a 10% market share. So percentage numbers are always like deceiving. But if you look at it, my sales numbers has actually increased, but on a whole, my market share has decreased. That's a point for another time. But what exactly went wrong with the Ola scooter, right? So multiple people speak about multiple things, but the primary problem, what started happening was that they were component failures, right? And why did the components fail? One of the primary reason people say is that they were not tested enough. So the longevity of the products was in question. And the second thing people talk about is also with respect to the temperature. So they say that they were running it for a pretty long time. Temperature started rising, products started failing. But all in all, there was another problem, right? Which was This was a company which decided that only thing which was important was growth, right? And they never thought about sales support. They never spoke about service, right? They kind of, gave too much of importance on growth. So suppose if they had a supplier who could supply 10,000, let's say, motor control units, 9,500 of it, or let's say 9,800 of it, went into new vehicles, right? And only about 200 of it started going into the service centers. I mean, that is still a spare part. You still need the same component to replace. So what Ola ended up doing was they thought they could build more, they could kind of like, grow the company. And once they hit a certain targets, then they could come back and do service and other things. But time has proved them wrong. And now I believe Ola is down to under 10% market share, actually speaking, while the market has grown. There are other players who have got in, there are other players who are growing steadily. Ather, which was basically like ridiculed when Ola was basically growing at that breakneck pace, Ather seems to be doing very well now. We have a new entrant. There are other people who are coming into the market. So now, what I'm trying to tell you is all of this, if you look at it, the Ford Pinto, the Ola electric case, or I can go on and give you a lot of different examples, right? So if you look at, I think the very first electric cars which were launched in India, if you remember, that was the Riva, right? So what was the problem with the Riva electric? Or recent days, I think you can speak about the problems which have been happening with respect to Citroen, right? Very well engineered car, but still not doing well in the Indian market. It is not that the product has to fail. It is not that the product is something like which catches fire, it breaks down or something. If you don't end up selling enough numbers, then I think you have lost the game. You have not built the right product. You have not built something which customers want, right? You have similar problems happening. Let's leave out automotive. Let's kind of go into some other space and probably look at it there. Take the number of AI companies which come up and wind up on a day-to-day basis, right? One thing becomes common, right? So what becomes common is the fact that this. Okay. What becomes common is the fact that failures are a way of life here, right? And a systemic study of failures, right? You study the failures, analyze the failures, right? And you kind of like use this analysis, you kind of use this learning to build products that do not fail. To put it very simply, systems engineering is a branch of engineering where I believe you'll have to start by studying what failures others have done. And using that failures, you come up with a set of rules, you come up with a set of best practices, which will make sure that your product does not fail. This is the simplest that I can do to explain what systems engineering is about. Now, you might think that, okay, this all sounds good, but where do I use systems engineering? I'm pretty sure you are using systems engineering every single day in your daily life as educators. Just go back 5 years, right? COVID 2020. How did we start education? How did we start educating people, right? How did we start doing our exams, right? And fast forward to 2021 or even 2022, when a lot of sessions were still online, right? How did this develop here? Maybe when you started off, you had a lot of failures. I know of people who passed only because, exams were conducted online in 2020. We call them COVID batch. I work in industry, I work in staffing, and anyone from the COVID batch, we are pretty reluctant, right? So we kind of knew what went on during that. It's a pretty well-known fact. But did we stop there? Did we just continue with the same Google Forms? Did we do that? No, I would say no, right? Pretty much everyone improvised. You started building better ways of doing it. And today, if I ask you, can you deliver a complete course online? Can you conduct exams online? And can you do it at scale? I believe the answer is yes, right? Now, I work with the work integrated learning programs at BITS Pilani, and at any point of time, we have about 48,000 students taking up various programs in the program in the whole department. 48,000, I'm not kidding, right? Something with a figure which still astonishes every time you think about it. And all 48,000 learn online, right? The classes are not offline, they learn online, which means classes are scheduled, classes are delivered. There are mechanisms in place to make sure the teachers do deliver the lectures to the best of their abilities. Then there are the exams which happens, online exams, offline exams, everything being consolidated. So what I'm trying to tell you is systems engineering, this is something which we have done quite a lot. We do daily in our life. We will have systems in place to make sure that our kids learn. We have systems in place to make sure our students do not indulge in malpractices during exams. We have systems in place to build vehicles. We have systems in place to make sure vehicles do not fail, right? So with that introduction about systems engineering, I believe I can probably jump in, and now I can start talking about what exactly is the right way to build a vehicle. Where do you start? What do you do? I think it's a pretty good place for me to start, right? So now before I move into the actual lecture here, or the webinar, like sorry, I don't think we should call it a lecture. So any questions with respect to systems engineering? Do you understand what this is? I know you're still not very excited about what systems engineering is, but as I start moving in, probably like I'm able to kind of like give a better understanding of this. So any questions before I start moving? To put it into perspective, systems engineering is the only way that you can get a team of, let's say, 100 to 150 people, right? Which is what is needed to build a vehicle. And these people are probably spread across 4 to 5 different departments. Sometimes departments sit in different geographies, which probably mean you speak in about 6 to 8 different languages, which are not your mother tongue. You probably speak English, but I speak Tamil. Someone speaks Malayalam. Someone speaks Telugu. India is a cultural melting pot, and we have more than 8 languages. But let's assume it's an international team. You have these type of languages which is happening, and if you ever think what is the only thing which ties everyone together, everyone works together, they deliver results, and they deliver it on time, and they deliver it without failure, or let's say like they deliver it to whatever like specs that we have, right? So the only way that we're able to do it is by going with systems engineering, right? And systems engineering, I'm pretty sure that I mean, if I ask you, most of you would understand some kind of a development methodologies. You would have spoken about PDLC, product development life cycles, software development life cycles. We speak about V model of development. We speak about waterfall, right? So these are things which pretty much a lot of us have come across. We have already done it. Or if today I ask you, hey, I want to develop a data logger for my electric vehicle, right? So how would you build it, right? So pretty much everyone starts with requirements. So you say that like any good engineering, we'll have to start with requirements. We'll have to understand what is needed to be built, and then once we have the requirements, then we would probably design, we would build, right? So this you can do it either in a waterfall method, which means you do it sequentially, or you have V model, right? Where you have the design activity here, you have the build activity here, and then you have the test activity. So that is the V model of development, which can also use virtual testing, right? So while you're designing your requirements, you can virtually, test if your requirements would work or not. So there are a lot of things that you can do as a part of it, right? So now this is one way of looking at things. This is one way of doing work. But of late, there is also a new methodology which has come in, which is called as agile methodology, right? So what is agile method? Agile method is you do quick iterations, you build things in a small loop, so that you are trying to build linearly, but you're not going one after the other. You're building multiple iterations, you're building MVPs, you're improving MVP, you're adding features. So in fact, one of the Outcomes of working in agile methodology is a role called as a product manager. How many of you have heard of this role? PM, right? So they call PM roles. And PM roles in FANG companies, right? So FANG stands for Facebook, Amazon, Apple, Netflix, Google, the high-paying companies. I think now you have OpenAI and Anthropic and other companies also come in. So a typical product manager in the US makes roughly about 300 to 800K USD a year, right? So 300K USD is like a super duper salary there. And the highest paid people are all product managers. And what do product managers do? They manage this type of a development of your product. How should it develop? What are the MVPs? How do we move forward? That's basically what everything is all about, right? So coming back to it, depending on whichever way that you choose to work, you might choose a different way of working. But one thing which remains constant everywhere is everything will start with requirement, right? So I hope everyone agrees with this. So without requirement, there cannot be anything. So you will need to start with a requirement, and that is basically how this is going to move forward. Now, let me try my luck and ask you a question here. Um, how did you start designing the powertrain? I'm hopeful that that's what you were doing yesterday, either using Ricardo or Simulink or Simscape or something. How did you start building out your electric powertrain? Did you actually do it? What did you start doing it with? What was the first requirement which was given to you? And how did you start? More often than not, someone would have given you a requirement like this. They should have said, hey, build me a vehicle which can go 0 to 60 in 5 seconds, 6 seconds, something like that. And you might have probably started from here. You would have either did some hand calculations, or you might have chosen to go with the model-based development method, and you would have started doing it in MATLAB Simulink. So, quick question here. Is this what you did, or did someone do anything different? Um, Please do indulge me, and if you can take a little time and this type it out in the chat box, would be really helpful for me to understand if I'm, connecting with you or if it is going above your head. Is this how you started? Is there anything that you did differently? A quick answer, something which kind of tells me that if I'm in the right track, right? So I'm assuming that so while you do post it there, let me just move on in the interest of time. There's quite a lot to cover. So I'm assuming that this is basically what you did. So you would have done your calculations, you would have done F is equal to MA, right? dV by dt and so on and so forth. And you would have probably figured out what is the size of the motor that you need, what is the gearbox that you need to do. Maybe some of you might have modeled it in Simulink, and you would have had a drive cycle come in, and you would have analyzed torque and force and what is the motor current even, RPMs, impact of RPM. There's quite a lot of things which you could have done, right? So I'm not saying this is wrong, but I'm just saying that this is incomplete, right? You have not completed it. It is not fully done. Because what happens is, while this is something which will work extremely well in Simulink, this is not how the real world works. So when we go to the real world, right, there is a very interesting thing that we need to do. How do you make sure that the product that you're building, whatever product, right? It can be a motor, it can be a vehicle, it can be a mixie, it can be a coffee maker, whatever the product or service that you do. How do you make sure that your target user is able to use it and he is able to derive the benefits from it, right? Very simple question. Let's say that I build EV, right? Two-wheeler. Leave out four-wheeler. It's a little difficult, right? Let's go with the two-wheeler. And the typical user, let's say, is a 18-year-old student, first year student, 18-year-old first year student, right? And he's now driving the vehicle. Now, sometimes what can happen is you can also have a 30-year something, right? an young professional, they are also buying the same EV. They are buying it because they want to save some money on, transport and things like that. They are buying it. And then there is a 20 plus something guy who's basically a gig worker, right? Now, if you really look at the people who might buy your vehicle, you will want all of them to buy it because that is when you sell more vehicle. And as a company, as a product designer, more people that buy your vehicle, that is one form of a success. You know that you are succeeding commercially. But there is one more thing which needs to be done here. Now, this 18-year-old guy, he's going to abuse the max out of the vehicle. He's going to try going full throttle. He's going to put two people. He's going to put three friends. He's going to try doing all of that. Right. So let's say that this would probably be a monkey in the wrench. I'll just write monkey here. I just want you to understand. I'll tell you why, right? Because this is a person who is probably going to do everything you advise them not to do, they will probably do that. So you tell them, please do not drive with full throttle for more than 10 seconds. They'll want to go try it. You tell them, be very gentle with the throttle. They'll try to do wheelies. You say two people is what pillion is. They'll put four people on the vehicle. A professional is probably going to be your ideal customer persona. Travels single or maybe a pillion, takes his kids around, takes proper care of the vehicle, brings it for servicing, everything happens. Now, on the other hand, the gig worker, right? They are probably not going to abuse it, but they are going to utilize 100% or 150% of the vehicle. They need the vehicle to be running day in and day out. They don't want the vehicle to break down. It has to work perfectly, and that is when they can actually make use of it. So now I mean, there are two ways of looking at it. Now, what you have seen so far, let's say that I saw one of Dr. Venkatesh, right? So, sir had said that you do a design calculation and then do simulation, whiteboard mathematical calculation, simulation, hardware implementation. Vijay Lakshmi ma'am has also mentioned the same thing. Pramod sir, sound is low. If others have a similar issue, could you please let me know? Or if it is okay, then probably you would have to check it. Seems okay from my side. So ma'am has also said you'll have to do a whiteboard calculation. So now what I'm saying is you might design and you might build it to the best possible specifications, but are you taking into account how these people are going to work with, right? Um, we will not. We do not usually, right? So now here comes the difference between what we do in academics, right, and what we need to do as the industry veteran. Now you have your Ola, right? S1, and let's say you have the TVS iQube, or let's say Ather to a great extent because the approach to engineering is more industry lined, whereas Ola is more startup lined, right? So they want to grow, they want to look at everything like a software company, but unfortunately, automotive industry is not. Though you do have software, there's a lot of other things you'll need to look at, right? So now, what is the difference between looking at it from an academic perspective? I'm not saying it is wrong. I'm just saying academic perspective in many cases, because of our focus on technology, it is rather incomplete, right? So I'm someone who works on both the sides. I work in the industry. I mean, I teach as well. So I kind of understand that there is a pretty big gap which comes in, and that gap is basically systems engineering. So now, how would I look at it from an industry perspective? So now, from an industry perspective, I would manufacture the vehicle for three passengers plus 100 kg load. Now, you might ask, hey, by definition, a two-wheeler can carry only two people and there is not supposed to be any load on it. But what are you doing here? You remember the Bajaj M80, TVS 50? I know it is a little old right now, but do you remember why these vehicles succeeded so much? right? By any definition, the Bajaj M80 should not have succeeded. It was based on a Hero Cub, Honda Cub. It was an underbone. It was a very rudimentary vehicle. But why did the M80 survive in India? Or for that matter, why is it that the TVS 50 is the only moped which we have? I think till date, from the time that it was launched, I think probably in the early 80s until now, right? Just imagine 45 years, there is just one vehicle which has survived in the industry, and that I think is the TVS 50. It has gone through a lot of versions. And right now you have a TVS 50, not exactly 50cc right now, it's probably a 75 or 100cc right now, but it is there in BS6, guys. Why does it exist now? Because of the way that it was engineered. It was not engineered for two passengers, right? It was engineered for three passengers plus a 100 kg load. I'm a part of an Indonesian OEM right now. We are trying to develop an electric two-wheeler for Indonesian markets. This is what we are doing. Our target weight for all the design calculation is 390 kilograms. This is the design weight that we have. This is before we implement any kind of a factor of safety on it, right? I'm not talking about factor of safety here. I'm talking about the design calculations without having any factor of safety in there. 390 kilograms is what we are taking as the load which might act on our electric two-wheeler, right? So the difference when it comes to looking at vehicles from let me say a whiteboard perspective and industry perspective is that we try to predict failures. We try to think about what are all the different ways in which some failures can happen. We try to think about what industry standards we need to be aligned with. We try to think about all the edge case scenarios. We think about pretty much everything when we design it from an industry perspective. So while it might have been sufficient to just do this from a whiteboard perspective, when we kind of try and go and do it probably into the industry point of view or industry perspective, there is quite a lot of other things which we add on to it, right? So while I will get into it, I'm just going to tell you what all we are going to be covering. So while we stop with the motor size and the inverter and the gearbox, when we go to the industry side, we do kind of go and start looking at something called as safety analysis, right? Hazard analysis, failure mode analysis, we go for supply chain, we go for tolerances. There is quite a lot of other things which we will start looking at, right? So let me tell you why that is important, right? Now, let's take the case of Toyota, right? Toyota, as you know, is supposed to be an extremely good manufacturer, very reliable manufacturer, but sometime around 2009, right, they introduced what is called as a drive-by-wire. I think now we are all very familiar with it, but Toyota was the first company to introduce it, and it was for IC engines. It was not for electric vehicles, so which means we had a ETB, electronic throttle body, drive-by-wire system. Unfortunately, what happened was this throttle body will get stuck, right? So the driver is only pressing a pedal. On the pedal, there is a sensor, right? Sensor goes to an ECU. ECU is then supposed to send a signal to the actuator. Actuator opens the throttle. Now, earlier cases, we used to have the driver directly operating the throttle by means of a cable, but now a drive-by-wire, right? So it's completely by-wire system. So now this is how it is actuating right now. So 2009 to 2011, Toyota had actually a failure in the throttle. So the throttle would get stuck. So the driver was letting go of the pedal, but the throttle is stuck. The vehicle will not slow down. It caused something called as an unintended acceleration. The people would take their feet off the throttle, vehicle is not slowing. They press the brake, vehicle is accelerating, and then brakes are also applied, which means the vehicle is not slowing down, brakes are overheating, brake failures are happening. There were a lot of accidents which happened. And in fact, Toyota didn't accept the fact that it is still like a problem with them. They just did a recall. They spent from $4 5 billion doing that replacement. But this was something for the very first time people understood that the moment you put some software, the moment you put electronics into it, you are no longer dependent only on one single thing. There are multiple ways in which the failure can happen. Until then, you had a throttle cable. If the throttle cable gets cut, your vehicle will not accelerate. All you do is find a roadside mechanic, put a new cable, or sometimes what we have done is, I don't know if you've tried it, but what we have done is we have taken the old broken down cable, we have tied it with rope ties, we have tried to do a lot of, on the fly things because we are stuck in the middle of no, I mean, I'm of course talking about 15, 20 years back. So there's a lot of things which we could do, but nowadays what happens is anytime you have a mechanical component, right? And this mechanical component is being controlled by electrical or electronics, let's just call electronics, right? And to drive the electronics, you have some software. Whenever something like this comes into play, we now have to start taking our safety into consideration. It is no longer safe. Earlier, a driver used to operate the mechanical system. So any failure which happens, the responsibility was purely with the driver, right? But now what happens? If something failure even happens here, the driver is not controlling this. The driver is controlling some kind of a pedal or some kind of a system they are controlling here. So which means now the responsibility will be with the manufacturer. Manufacturer will kind of get sued. Manufacturer will kind of probably get into lawsuits. Lawsuits in US can destroy companies, right? So now, for the first time in 2009, when this problem started happening, that is basically when we started taking safety of systems into consideration. So we started calling these systems throttle pedals, brakes, steering. We started calling these systems as safety critical systems, right? And to understand if a system is safe or not, we started doing something called as functional safety. We actually started figuring out what functional safety is. How do we decide if it is safe? Can we write this piece of software? What will happen if, in case there is a corrupted CAN message? A CAN message goes to the motor and says, hey, brake is applied, you cut your torque. But what if, in case that CAN message gets corrupted? Can a CAN message get corrupted? Yes, it is very much possible. Electromagnetic interference can corrupt a CAN message, right? Or some node can fail and it can fail to relay a message back into the motor controller. There are multiple ways in which this can happen. But ultimately, think of it, right? What is going to happen when the driver lifts the accelerator pedal and your torque is not going to stop? What if your torque does not fall? What if your vehicle is continuing to accelerate? That, if you look at it, you would understand that it is no longer possible for us to just be, complacent and probably say that, hey, you want this? Okay, let me just do everything and give it to you. We cannot stop there. We'll need to take the next step after this and we'll need to tell them, okay, the vehicle will operate and it will go from 0 to 60 kilometer per hour only if throttle is pressed. I mean, of course, goes without saying, but only if throttle is pressed. But even if throttle is pressed, suppose knowingly or unknowingly someone touches the brake, then none of it will happen. It should basically shut down. You should not give torque. Or the driver is pressing the throttle, your vehicle is accelerating, and while it is accelerating, you see that the motor temperature is kind of raising towards the upper limit, or the battery temperature is raising towards the upper limit. Will you still allow this 0 to 60 kmph to happen, or should you do something different? Right? So that's basically what we are going to do. So we are not going to stop with, whatever requirement that we have. We are not just going to say that, okay, hey, this is all it is. I've kind of figured out what is the motor you need, what is the battery you need, what is the inverter. We are not going to stop with that. We are in fact going to go one step further. We're going to do a HARA analysis, hazard analysis, and something, right? You can search upon Google. Or if the same thing is to do with cybersecurity, we do a TARA, right? TARA is threat assessment and recovery analysis. HARA is hazard analysis and hazard assessment and recovery analysis, right? HARA and TARA, you do that, you come up with some safety goals. So now what you do is you tell them, hey, in case something like this happens, then you'll need to have a fallback strategy. So allow the vehicle to accelerate 0 to 60 kilometer per hour in 6 seconds only if motor temperature is less than 30, battery temperature is less than 25, if the brake is not pressed, if the vehicle is completely safe, there is no errors, blah, 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 blah. Put everything in, and that is only when you will actually act on it. So, what it basically happens is you might have one requirement which is 0 to 60, but when it passes through all of this, you might end up with multiple different requirements at a VCU level. From the VCU, it will also go to the inverter level. And it is not just sufficient that you just tell the VCU that check the temperature before doing it, or you tell the inverter check the motor temperature and then do it. No, you don't stop there alone. You also make sure that you are validating it, right? You'll need to prove that this safety goals are met. And only if you do that, you can deem the vehicle to be safe to release to the public. Now, going back to my original condition, do you really think the Ola S1 went through such a rigorous process? If it had gone through the rigorous process, should they have not caught out all the problems? Let's say they say that, okay, we need to have the vehicle to run trouble free without 1 lakh kilometers for 1 lakh kilometers, right? How do you validate that it is running trouble free for 1 lakh kilometers? You should have taken your scooters, you should have driven it on the road for 1 lakh kilometers, not one scooter. You drive maybe 10 scooters, 20 scooters, you drive some in Madurai, you drive some in Leh Ladakh, you drive some in Rajasthan, some in Kolkata, some in Chennai. You drive it in all the different places across all different locations you might sell your vehicles to. Run every vehicle for 1 lakh, 2 lakh kilometers, run it 24 bar 7, and then you understand if the vehicle is proper or not, right? And unless you do it, you do not launch the vehicle, right? That is the thing that most people do, automotive OEMs do. But when someone tries to sidestep all this and jump in front and then go and launch it first, these are the problems that you start inviting to yourself, right? Which kind of brings me to the very first topic that we are going to be discussing. I mean, don't worry, like if you're not able to completely cover it, I anyways have the session tomorrow as well, and I'll kind of like try to continue from here. So time is not exactly a constraint. Um, Let me just quickly check into the chat window. We try to do approximation for simplicity, but in industry, we go for all failures and disturbances. There's a large gap between academics and industries. Yes, so my whole point is to try to help you see where those gaps are. So these are the gaps that I believe you should be spending your time researching. So if you try spending your time researching there, then I think that's something which can probably bring in a lot of new things which we can probably do there. So just give me a second. Yeah, sorry about it. So let's now jump in. Let's start looking at requirements. So what are we talking about in terms of requirements? One of the requirement I showed you, but how do we go? What is the way in which we'll have to do? Let's go ahead and start looking at it, right? There's not a systems engineering discourse per se, so we are just looking at it at a very high level. But if in case someone wants to go deeper into it, I would suggest you to go look at in systems engineering 15288, right? So that's basically what you need to be looking at for understanding this. So we had this requirement which said 0 to 60 kilometers per hour in less than 6 seconds, 150 kmph top speed, 400-kilometer range. This is a four-wheeler requirement. It's not a two-wheeler requirement, right? So now what we should basically be trying to do is once we have this requirement, we should first try to the very first process that you do as a part of systems engineering is something called as requirements engineering. I mean, requirements analysis is something called as requirements engineering. So you take a requirement and you start breaking it down, right? And breaking down, we kind of do it in two, three different ways. It's not an easy job. There are a lot of things which needs to be done. But let's assume that you have the vehicle level requirements. Sometimes you will have functional requirements, right? Sometimes they'll just want to benchmark. So benchmarking is the process of taking a competitor's vehicle and understanding how their vehicle works, stripping it down, figuring out what component goes into it, and then your product is supposed to match that exactly ditto, right? So that is benchmarking. So people do that as well, or you'll have to exceed it. So now suppose you have got a vehicle level requirement. How do you break it down, right? So what I'm going to do here is I'm going to break it down into system level requirements. And within that system, there are multiple components. How do I break it down into component level? And some of these functions, it might not be realized from purely a hardware. I might want to have some software requirements as well. So how do I do that? What goes into which area? We'll need to start looking at it. But irrespective of whatever we try to do in terms of requirements, every single requirement should have a way to test it, right? So you will need to be able to verify it. So verification is at an individual level, validation is at a higher level. So here individually you are verifying it, you are making sure that it's working as per your specification. Validation is at the final level, it's at the top level, right? So I hope you understand the difference between verification and validation, right? So validation is checking if you have built the right product, right? Verification is to check if you're building, if the product is being built right. So the difference is, are you following all the principles? Are you doing it in the right way? So that is basically verification. But validation is, do I have the right product? I wanted a scooter, but you have given me a bike. That is validation's headache. Verification is, I wanted 50 kilowatts. Did you give 50 kilowatts? I wanted 20 kilowatt hour. Did you give 20 kilowatt hour? That is verification. Of course, there could be something on the validation side as well, which might say 400 kilometers range or 150 kmph, but those are validations, right? So that's over here. Whereas at individual levels, we will do some verifications, right? So every requirement must have a verification. A combination of requirements might even have a validation, but you will need to make sure that you're able to test it. Now you might ask, why do we have to do all this testing? Can't we just, have the requirements? Can't we build it and can't we go test it? Unfortunately, the answer is no, right? So if you look at the cost that it takes to fix, right? I'll just say the cost it takes to fix and your life cycle, with what part of life cycle you are in, right? So you start at requirement stage, you go to high level design, you go to low level design, you go to the implementation, right? And probably integration, and you go into your testing stage, and this is your production stage, right? So the cost that it takes for you to fix mistakes, right? So I'm not saying mistakes, it can be bugs, it can be gaps, right? Whatever it is, you have genuinely are not understood. So that is something which kind of goes like this, exponentially higher when it goes to production and extremely cheap when you're still in design stage. Even at low level design, it is still something which is easy to fix. So which is basically why if you look at V model, We have those, the virtual testing which happens. Our agile methodology, they focus a lot on this. So before it actually goes into production, you have multiple sequential runs being done. Of course, you cannot build a car in agile, but the software can be built in agile, right? So you'll need to kind of figure out what is the best way for you to capture these errors way before they end up in production, right? So that's what we're doing here. And the reason we need to have different methodologies is to test different versions of what you're developing. Suppose you have written a piece of software code, right? So the code alone, if you have written, you could just do unit test, right? You could just have a test harness, you could just do unit test. Now, suppose if this code is going to sit in a microcontroller, right, you'll need to do a software in loop test because you don't have a complete thing built. So you kind of do a in loop test. Now, suppose this microcontroller is now needing to go into a full-fledged hardware, right? Let's say in VCU or a VCU or something, then you go to a hardware in loop specification. Then it needs to go into a vehicle, but the vehicle is still not ready to go into the road. You do a dyno test, powertrain bench. I mean, because we are talking about it here, we do it on a dyno. And finally, when the vehicle is built, all the components are built, suspension is built, we actually put it into a real vehicle. We go to the road and or the track and then we test it. So depending on what you have, at what point you have, you should be able to kind of look at various different ways in which you can test your requirement. But that being said and done, these requirements are not exactly some things which are written in stone. As in, I'm not saying that just because I have mentioned 0 to 60 in so much of time, you have to stick to it. I'm not saying that you will get 400 kilometers range no matter what. I can say WLTP range of 400, actual range would be 300. I mean, if you look at all the EVs, they will say that the WLTP range is 500 kilometers, but it would actually do about 350 to 370 because this happens to be an ideal case scenario and actual scenario will be different. You accept it. You have an LFP battery, right? And LFP batteries kind of needs to be extremely temperature sensitive. And the moment that you start like going into extreme cold climatic conditions, it'll start losing capacity, it'll start losing range, SOC drops. A lot of things like that starts happening. NMCs are better, slightly better that ways. They have more energy density, but they are much more thermally sensitive than what LFPs are. So you kind of need to come across some kind of a compromise. You'll need to figure out what you're doing. And that is basically what we are trying to do here. So now what happens if it's a 45 degrees centigrade, or you're going up a mountain slope, or your battery is dead, battery is at 10%? Do you still need to meet the 0 to 60 in 6 second requirement? Answer is no. So which means your requirement is not usually, most of the cases, requirement is not usually a fixed point, but rather it is an envelope. So you say, provided the temperature is 30 degrees, provided you have more than 50% SOC, provided you are on a plain piece of road, then you can go meet your requirements. If not, you're always willing to relax it. Now, suppose if you don't relax this condition, suppose you say, okay, there can be no relaxation possible, you will have to meet it, then what is the only way that you do? Right? I think this is something which Suchi had also asked you as a question before we started. Would you choose a motor which is? I mean, I'll ask you the same question, right? Okay, let me circle back. Let me ask you the same question. So, what we need to do is, if in case you can't relax, then you'll need to kind of oversize the motor, or you'll need to oversize the battery. Um, both of these things would always come at a cost. So if you need to kind of like have the cost also to be like taken into account, then you either accept derating, right? So you say that as a requirement, you say it does 0 to 60 in 8 seconds under extreme conditions, right? So the customer should accept it. So they're like, no, no, they did declare it, they didn't say that. Or you kind of relax it, right? You say that. put a small star and then say conditions apply. So you can do something like that, right? So now let's kind of dive a little bit more deeper into it. So I'm just gonna kind of like take you through um, what you might have done as a part of your academic approach towards it. So the moment that you say that 0 to 60 is this, you have some vehicle information, you have some tire size, then you will probably go through a sequence of steps, and you would probably find out, okay, I'm kind of like recurring a motor which would probably be able to carry 340 amps as a peak. So usually the generally accepted condition is if 340 is the peak, then somewhere about 150 amps, nominal 100 to 150 amps is basically the nominal or the base current which you work with, right? So you do not always accelerate. So 50% is basically what we do. Now, this is where we start with, right? So which means this is going to be our baseline. But once we have the baseline, then we start like modifying these numbers to kind of start meeting our safety requirements. You start doing it for thermal requirements, NVH requirements, and a lot of things like that, right? So let's say from a safety margin, we say an inverter might be rated for 2x the nominal or the peak current. So if you have, usually when you go for hardware design, if this is 340 350 amps, then I would choose my components capable of withstanding 700 amps of current, right? So my MOSFETs can, and all those things, I'll kind of go with 700 amp capability. So now if I mean, of course, we haven't taken what is the voltage here. So let's say that if for whatever reason this proves to be too difficult to achieve, then I might, maybe let's say like this is, okay, we have not taken voltage into consideration here, but let's assume that this is basically happening at 96 volt. I might consider moving up to 200 volts, right? So going up to 200 volts, I can probably drop it, which means my components can be now designed for 350 amps, which would probably be a little cheaper. Efficiencies are higher because now I'm working at 200 volts. Could work, right? I'm not saying it will, but it could work. So I can kind of try doing these type of trade-offs. Now, when we come into the actual trade-offs, right? So now let's say that I'm trying to look at 96 versus 200. So what are these trade-offs that we'll have to do? And what are the kind of like compromises that we might actually end up doing, right? Let's pay a little bit of an attention here, and I think this is where Suchi's question comes in. So you have three different motors, right? So one is a IPMSM, inner magnet PMSM motor. There is a SynRM motor, and there is a induction motor, AC induction motor, synchronous motor. Now, obviously, looking at it, you see that the AC motor has got the least efficiency here, right? Power density is also less, right? Now, what would you probably choose for your electric vehicle? Now, there is a very interesting thing which is being developed, which is kind of developing everywhere. Okay, now let me not divulge what it is, but let me go ahead and ask you this question. What motor would you select? Weight of motor would be more of design oversized, space required will be more. Yes, Mr. Ravindra, like it is extremely right. And in fact, one of the, I mean, I'm just waiting for you to answer which motor you would select. I'm holding you on to it. You kind of didn't answer it when Suchi did put it up. So I'm going to ask you the same question. Go ahead and let me know what motor you would use. But in the meanwhile, I'll just ask the questions in the chat window, right? So something which kills electric vehicles is basically factor of safety, right? So we design with a lot of factor of safety, and the factor of safety keeps pushing our weight up, it keeps pushing our cost up, and as a result, we kind of ending up not being competitive, right? Many part of India, it is observed that if temperature goes beyond 40, electric vehicles becomes explosive. Is there a provision designed to cool the vehicle temperature? Yes, okay. Let's come to that, right? So suppose you are seeing thermal runaway, right? So what you're describing is Vaishali ma'am. So it's called thermal runaway. So if you do have thermal runaway, then you would have to bake it into your product. Most of the vehicles where this happens are vehicles where you kind of like either run with an NMC battery chemistry, or you kind of like buy batteries from sources which do not follow a lot of quality control, which do not implement systems engineering. But I would be very surprised if you find the same happening with, let's say, an Ather or a Suzuki EV or a Toyota EV or a Hyundai EV for that matter. You would probably not find this happening a lot, right? I mean, there will, of course, be a one-off incident which happens even with this, but to a large extent, this is basically controlled by very careful battery pack design, by implementing cooling into the system. In fact, for the EV two-wheeler that we are designing, we have both passive and active cooling systems which are there. We are running it in Indonesia. Indonesia would probably be even more hotter. So yes, we do need to take some considerations for it, which is thermal considerations. So now coming back to the motor choice per se, synchronous, SynRM, PMDC, PMSM. So now the whole question is, I come from a place called Coimbatore, right? I mean, I live in Coimbatore, and Coimbatore, I think I can go out on a limb and say this is basically the motor capital of the world. I mean, of India at least, right? Every nook and corner, you have someone making a motor or a pump. I mean, of course, there are other industries, but we do make a lot of motors and pumps in Coimbatore. So now, if I am from Coimbatore, and if I have an order to supply 5 lakh units each year, or something like that, what do you think would give me the cheapest cost, right? See, Sinaram, not many people are manufacturing. People do not have the technology to do it. Only Tesla does it at scale. Now, you might say IPMSM. Now, you can import it from China, but look at the quantities I'm talking about. 5 lakh units a year I'm sending, and even for once, right? If there is a strike in China, or if there is something like Mr. Modi and Mr. Xi Jinping, they have some war of words, and they say, or Mr. Modi says, okay, from now on we are putting an extra 20% duty on Chinese made products. What will happen to me, right? Every month I'm importing, let's say, close to about 50,000 units a month I'm importing. And if my cost goes up like by, let's say, $1 or $2 per motor that I import, every month I've lost about $80,000, $100,000, right? That's not something which I can withstand. And what also happens if in case China decides that, okay, we'll not give you rare earth magnets, right? This is where it comes in. So we do not always choose it based on what we see here, right? This is not what I look at. I also look at something beyond all of these specifications. I look at where I can source motors. I can source 5 lakh units of motor every month from Coimbatore. They have that kind of a capacity. And since these motors are manufactured at such a large scale, I mean, it goes to all the pumps and fans and a lot of things like that, I might probably be able to get an extremely good price point. Suppose something goes wrong with the motor, I'll have replacement, I'll have service, I'll have quite a lot of thing which goes in. So in fact, what we have done for our electric two-wheeler is we have gone with an AC induction motor. We have not gone with a PMSM. Indonesia does not have as much high taxes as India for Chinese imports, right? They're still little open to China, but we've still gone with induction motors. The reason is not that we wanted to have, something where, I mean, of course, Coimbatore, but it's still being sold in Indonesia. But the point is that we wanted to de-risk our supply chain. We wanted to look at a future where we are not dependent on magnets, we are not dependent on rare earth materials. We look at sustainability, we look at recyclability, right? There's a lot of things which goes in at a corporate level, and in fact induction motor is what we have used. Now if you look at Tesla also for a Model 3, um, they were initially on IPMSM, now they've gone to SINRM, right? But this the data from a while back. So what they've done is they've gone with an IPMSM on the rear axle, which is the primary drive motor, right? 95% of the time it is used. And during extremely heavy acceleration or torque vectoring or something, that is the only time the front motor, this is for the all-wheel drive version, that is the only time the front motor is used. And the front motor happens to be a AC synchronous motor, right? They've gone for an induction motor there. They've kind of like not gone for a PMSM in the front also. That's basically because of two things. So the first one is, there is a little differentiation which happens in terms of supply chain shocks and things like that. But the primary reason is whenever the motor is not running, right, your permanent magnet motors, they'll always have a drag because you have a permanent magnet there. Even if you're not energizing your rotor, I mean, because yeah, the rotor has got a permanent magnet. Even if you're not energizing your stator, there is still going to be eddy current losses. So which basically means even when the motor is not running, there would have been a drag if you had gone with a permanent magnet based motor. Whereas now when you've gone with an induction motor, absolutely no lag. I mean drag, right? So which means both the wheels freewheel, and if it is freewheeling, then it means that you have kind of pushed your efficiency of your vehicle as a whole, right? So there is a trade-off which has come in here. You are accepting a low efficiency motor, you are accepting a low energy density motor, but on a whole, as a system, this motor works better. The motor is kind of like helping you like reduce the parasitic drags among other things, right? Okay, cooling for EV two-wheelers. Right now, what we have done is we have gone for a PCM, a phase change material-based sleeves. It's a pretty new technology, and we've also gone in for chilling plates, liquid cooling. And in our case, what happens is we have an integrated power module. So our power module is it's kind of a little weird when you look at it. So what happens is you have the battery pack which sits here, right? And on top of the battery pack, this is basically where all your inverter and other electronics sits here, and then on top of it sits your DC-DC, right? Inverter and onboard chargers, these are integrated. Or okay, onboard charger is here, and DC-DC and inverters are over here. So now we call it as an integrated power module. So we have this here, the battery packs. So they have some phase change material sleeves, and this whole thing is also chilled, right? So we have chiller plates here, and we have liquid cooling which we use for this as well. So we are actively managing it. We have also placed it right. There's the front wheels, right? So we've also placed it right behind the front wheels so that there is going to be some active cooling. I mean, aerodynamic cooling, which is also possible. But that is not just sufficient, right? You need to kind of like look at various other aspects of it as well. So, I mean, this is in response to the question Mr. Rojo Kurian had put it up there. So, most importantly, what we do is in this case, we limit our charge and discharge to 0.5 C, right? So, which means, the thermal gradient because of the internal resistance, we are trying to restrict that to a great extent as well. So that is basically how we are controlling it. Any other question? Sorry, like I keep getting calls, so just had to put myself on mute. But let me kind of like just try to complete a couple of slides. And Mr. Vrijesh Rai, like I'll just come to your question. Develop a systems engineering model for early prediction of failure. I'll kind of quickly come into it, right? Let me quickly come into the questions, but I hope you're aware of the fact that requirements cannot be written in stone. Requirements will always be something which we will trade off on, right? And we definitely need to do it in order to make sure that we are able to meet our we are able to meet quite a lot of these practical considerations. Now let's quickly look at one more case, right? So where we are building a electric vehicle predominantly for using inside the city, right? So now let's say that we have a very strict target cost, right? And now we are not going to be going with IPMSM, right? And we need to kind of like go with some other motor, right? So let's say that, I mean, why not PMSM? Because of rare earth minerals, right? So if you remember some 3 4 months back, Xi Jinping could hold the entire automotive, American automotive. They could kind of hold them responsible. They could kind of like threaten them with a lot of things just because they said we are not going to allow for rare earth materials export. Now, rare earth materials, it's not just about mining, but it's about how do you grind it, how do you make it into motors, I mean, how do you make it into magnets. So that is basically something which is going to be extremely difficult, and the only companies which have those technologies are companies which are in China, right? So that's the supply chain side. So now, what would we do on that, right? So suppose now we have gone with a Sinara motor. How do you kind of like still optimize your system with this, right? So you'll need to kind of start looking at those aspects as well, and that is something which we have tried to figure out here. Now, this is not just from a hardware side. We should also start thinking about it from the controller side, right? So controller side is going to be a little difficult, right? I mean, I'm not saying that it'll be pretty easy for you to understand, but what I'm trying to tell you is instead of a inverter whose only job is to control your motor, right? Now, what you need to do is you'll need to kind of like have a vehicle control unit. You'll need to have a torque monitoring function. You'll need to have a Hara analysis done on it. You'll need to have fail safes. So you cannot use one single sensor on the pedal. You'll need to use probably two sensors. You'll probably need to put some extra software applications. If extra applications goes in, then maybe you're having to go with a slightly larger microcontroller, right? So what I'm trying to tell you is moving from our basic function to going to a point where we are not just delivering the function, but we are delivering it in a very safe way. We are delivering it in a way that no matter, you remember the term monkeys that I used, no matter whatever monkeys are there, we are still able to get our product to perform really well. So that is basically what adds the costing to it. Now, you would have noticed it whenever you would bid for projects, right? So you would have projects from DRDO, you would have a lot of those projects come in. So, so I'm pretty sure that when you prepare a quotation for, let's say, you want to, bid for a project which makes um, a control unit for an EV, or let's say they're just saying, okay, hey, build us a EV powertrain. So an EV powertrain basically means that you give the motor, right? You give the motor controller, you probably give the battery, you probably give the BMS, and they also say you'll need a VCU or a display. So they say this is how we do. I'm pretty sure when you work it out from an academic perspective, you might say 10 lakhs, right? And you would say 6 months. If they come to me as a startup, I would probably say 30 lakhs and 6 months. If they go to a tier one supplier, right, value or someone, they would probably say 300 lakhs and 12 months, right? You see the difference which happens here? Does this mean we will not do a good job as academicians, or does it mean that we will not do a good job as a startup? So, what is the primary difference between the two things? Why do you think that a startup needs to charge so much, whereas a tier one like Bosch or someone will charge 10 times what I quote? What do you think is going to be the difference? Why do you think they quote it? Any idea why they do that? Right. So the difference basically comes in because of the number of extra requirements they add, the number of extra safeties they put into it, the number of standards they are compliant with, number of certifications they'll have. So pretty extensive, and of course that'll kind of like cost extra, right? Now let's say that, I mean, so what it says here is, in order for you to implement a safety critical function, it's estimating that you would spend about 2 million euros. NRE is like one-time engineering cost, right? So it is non-recurring engineering cost or something like that. So what it basically means is this 2 million gets divided by, let's say, 10,000 pieces or 20,000 pieces. This has to be divided and it has to kind of come up here. So which means your engineering cost essentially goes up, right? So there's going to be a lot of add-ons which comes in over here, and that is something which basically increases the cost for you. But does it mean that these are some things which we can do away with? Is it something that we can say that, okay, we no longer need it, we don't have to do it? Depends on the the buyer that you go with. Sometimes you might go, sometimes you will have no other choice, but you will still have to work with it. Let me probably skip this portion, right? It's going to go too much into hara or something. So let's probably skip this portion. Let me quickly have more testing and validation. Yep, right. Um, okay. Let me skip this, right? Primarily because it's going to take us through a very different uh, you know what is the time right now? 7:30. Okay. Maybe you can just tell me a quick thing. Do you really want to go into the safety thing part of it right now, or we can also try to do it when we come back tomorrow? I can probably try to spend a little bit more time on hara and tara, right? So that ways we'll have a lot more of time to look into it. But let me just put it this way. Uh, it's basically how you start breaking down your requirement and how you start coming up with safety goals and things. I think I'll handle it tomorrow, right? As a part of the battery, we'll take a requirement, we'll break it down. I mean, of course, that is, if you think that is still interesting to you, I'll tell you how you can come up with safety goals among other things. Is it okay if we do that? Right. So I'll just assume that. So now one of you had asked a question, how do we predict failures, right? And how do we know that this is basically how we make a product more reliable? So the simple answer to it is, if you can predict your failures, right? And you design or you mitigate, you end up with a reliable product. So can someone tell me what is the difference between the two? You can either design a product to be reliable, or you can design mitigations to make the product reliable. There are two approaches to making reliable products, right? So I would kind of say, I mean, I might be wrong, I'm not an expert. I would say this is the Japanese way and this is the German way. So, what is the difference between a Japanese way of making something reliable and a German way of making something reliable? Again, this is just from my experiences. It doesn't mean that that is how they do, but my experiences. Now, suppose you have two cars competing in the same price range. Okay, let's take two cars competing in the same price range. Um, let's take the Toyota Land Cruiser LC 300, right? Roughly about 2.5 crores, right? And BMW X7 also 2.5 crores, right? One is Japanese, one is German. So now in Japanese engineering, right? what they kind of follow, I mean, it's a pretty weird thing they do. So they do something similar to Yagna, right? This is a software design architecture design philosophy that we use. I don't know if you guys are familiar with it. So Yagna stands for you ain't gonna need it, right? So it just basically says you ain't gonna need it, right? Uh, Yagni, not Yagna, Yagni, right? So now what Toyota has done is they looked at the Land Cruiser and they said, okay, sunroof, right? They said, no, you don't need it. Why do you need a sunroof? You're probably going to drive your car in India or in Middle East, or you're going to do somewhere where it's going to be hot. So no sunroof. You want air conditioner, right? So we'll give a large air conditioner. But do you want to put touchscreen? They'll say no, no touchscreen, right? Have dials, right? And the dials, let's say that every day you use the dials 5 times. Every day, suppose you're driving the vehicle every day you use the dials 5 times, then they will design a dial which can do 5 times every single day for 20 years. So this is the cycle life they will look for when they're purchasing a dial. I mean, a knob, not a dial, but a knob. You have a switch, 20,000 times it has to work. Everything is being designed for 20 years, 30 years lifespan. You want suspension, what is the tube size you need to use? Make it 2 times larger, put it there, right? You want to have electronics, whatever is the minimum one, use that. Whatever you don't want, push it out, right? So Toyota is something where they follow the despite the user philosophy. So which means even if you don't maintain these cars, right, even if you go ahead and abuse the hell out of them, you know that almost 90% of the not 90%, 100% of the vehicles which were being used in the war zones were Japanese vehicles. Very rarely there were some Tatas in the mix, but very rare. If you look at it on a whole, the entire mix of vehicles were Toyotas, Isuzus, and Mitsubishis. No other vehicle. You won't see a BMW pickup truck or a Volkswagen pickup truck doing duty in a war zone, in a very dusty environment. You won't. Because what BMW and those Germans believe is that you have a maintenance schedule, right? And if you can go for a very, very strict periodic maintenance, every single oil changed, every single checkup done, everything done as per spec, then this car will also last you for 20 years. I mean, I haven't seen it last for 20, the modern day BMWs, but if you have maintained it properly, yes, they will still last. I've seen Mercedes Benz's. I mean, a friend of mine still drives an 80s Merc, right? I'm not sure 2020 Merc if it will still last for another 40, 50 years. But what the Germans do is they go with a maintenance-based philosophy. So they say, if you maintain it, if you mitigate all the failures, it will be reliable. The Japanese, they say we will design it in such a way that even if you don't maintain, it will still be reliable, right? So there are two ways of approaching it, and irrespective of whatever way you approach it, one thing which does not change is you need to kind of predict why the failures can happen. You will need to predict how the failures can happen, and you'll need to kind of make sure that you are able to mitigate those failures. So, which is one of the most important, activity that you would do engineering for an OEM, which is design failure mode effect analysis, right? So the failure mode and its effect, you would go ahead and analyze it. And when are you analyzing it? You're doing it at design stage. So before you even have started implementing it into a hardware, you'll do a DFMEA. You will do a DFMEA for hardware plus software. You will do it for mechanical components. You will basically do it for all of these things so that you understand what are all the failure points, and how you can mitigate those failure points, right? So that's basically what we see here, right, which is called as DFMEA. So how do you go ahead with DFMEA, right? So so what you do is you start by asking the question, how can this design fail, right? That is the first thing. So let's say that your motor, right? Let's just take this question. Your motor is producing 185 Newton meters. Suppose this is the rated thing. So now we'll say, how can this motor not produce 185? Let's say, how could this design fail? Let's say bearing failure happens. Let's say you have a short circuit internally. Let's say Hall effect sensor failure, water ingress. There can be multiple failure modes, right? We kind of like list out all the different failure modes which you can think of. How much can you think? 5, 10, 15, 20? Where do you stop? Let's say like 20 is a good number. We'll try to list out 20 different. Suppose you can't list out 20, then well and good. It means that your product does not have that many failure modes. It's pretty good. And once you do it, you try to come up with something called as an RPN number, right? So what the RPN number basically tells you is it tries to map out, I mean, see this severity, occurrence and detection. This is something which keeps on coming in the safety, safety things. So what we try to do is we try to find out if a bearing failure happens, how severe would it be, right? How severe do you think it is on a scale of 1 to 10? Bearing starts to fail, will it immediately fail or will it gradually fail? How does it happen? Right? I would probably say severity would be 3. It's not very severe. Even if a bearing completely ceases, then the motor might have problems. But usually, like before it reaches there, there'll be a lot of noise and things like that. So the severity is basically less. How likely is it that a bearing can fail? I've used SKF bearings, I've used the proper design, I've overspecified it, over-engineered it. The likelihood of occurrence is 2. How do we detect it? Can we detect it first? Yes, you can detect it. How do you detect? Anytime the vehicle is running, you'll hear it. Or if it is a very complex product or something where the motor is sitting inside the vehicle, I can put a simple microphone sensor or a vibration sensor or a MEMS for microphone or something there, which will detect the bearing failure. Or I can also kind of like monitor the current which the motor draws. And anytime the bearing failure starts happening, the current draw will slowly start increasing. So can I detect it? Yes, I can of course detect it. Now this will have a very low RPN number. It will have 6. So like that, it's not just for it, but keep on adding everything. And you try to find out what is the total RPN number for your motor, right? If it is less than 60, then you accept it. If it is more than 100, then you'll have to go for a design change. Now, let's say that I'm getting a China motor, and let's say I end up with 110 as the RPN number. It basically says you're asking for trouble. Do not go with it. You will probably have to kind of like think of something else. 60 to 100 have some additional controls. Now, let's say Chinese motor is at 60. So now what will I do? It is not very safe, or let's say 80. It is not very safe, but what will I do? I'll put a microphone. I'll try to check if everything is working fine. I'll try to have a very sensibly tuned motor control unit. I will not try to push the limits of performance. I'll try to keep everything under control so that I do not experience too many failures with it. Right. Now, similar thing, you can also go do it for your the unintended acceleration, right? So how do we kind of like figure out like how to map out the failure points here? So here we are taking the torque delivery and we are saying where exactly can things go wrong with respect to the torque delivery. right? So the DFMEA, you can either do it at a component level or you can do it at a function level, right? Even at a function level, it can still work. So this becomes another DFMEA. So how does the torque transmit? You press the pedal. From the pedal over CAN, it goes to VCU. From the VCU, it goes to inverter. Inverter, there is a power stage, goes to the motor, goes to the gearbox, and then goes to the wheel. Now, at every single point, what are the failures which could happen? And once you understand the failures which can happen, you can try to see how you can mitigate it. Like, say, for example, on the pedal, instead of one single sensor, you have two different sensors. So one sensor reads from 0.5 to 4.5 volt, right? The other sensor will read from 4.5 to 0.5 volts. It's inverted sensors, inverted pair. So once the VCU gets it, it will compare both the sensors, S1 and S2. They have to correlate. Only if they correlate, then you basically know that both the sensors are working. If only one sensor is working, then the VCU knows that there is something wrong. It will immediately say, limit the torque. It will not give you the full torque. It will limit it. But if both of it is okay, then it goes to the next one. Now, why should you use CAN bus? Can't you directly wire these sensors to the VCU? Why should you use a CAN bus? When you use a CAN bus, this CAN bus is fault tolerant, right? Whereas when you use these two sensors, you wire them directly to the VCU, they are not fault tolerant. They are susceptible to EMI, EMC, right? Some faults can happen, but whereas a CAN bus is more tolerant to it, right? So then it come to the inverter. So in the inverter, what we do is, if in case there is a software bug, right, we have a timeout. So what it basically says is every 100 millisecond, the VCU has to send a torque request to the inverter. If it is not able to do it in 100 milliseconds, then the inverter understands that there is a software bug. Inverter will stop working, right? So like this, we build um, reliability into every single aspect of the components. Every single point in the path, we try to figure out what could be the reason, and we of course go with RPN numbers for it, right? And here in this case, we find that, I mean, for an inverter thermal runaway, we find that if you don't have monitoring, then there is a lot of ways in which failure can occur. Whereas if you have a monitoring, which is a very simple temperature sensor, not the inverter, but the VCU is basically monitoring the inverter's temperature. And whenever the inverter temperature goes above a certain thing, VCU will cut off. You have a monitoring built into it, then you kind of like can reduce the RPN number. If in case you don't have a monitoring, then your design risk goes up. So which is basically why every single inverter will now ship with a temperature sensor. It's not that you're trying to make it more complex, but you're trying to kind of make it for a safety perspective, right? Now, this is not something which is that theoretical. This is something where we have seen this happen on and on and on again. In fact, the inverter failure is one of the reasons which is attributed to all us problems. Quite a lot of vehicles, they do see like inverter failure happening. Inverter failure does not mean the complete inverter fails, but capacitor is usually one of the first component which fails. Now, if they had done the DFMEA on it, I'm pretty sure they would have been able to capture it, right? So what does DFMEA do? It kind of helps you predict where the failures can happen. And when designing itself, you go and make sure that even if the failure happens, nothing will happen to it, right? So that's kind of like how we do it, which is you expect everything that can go wrong to go wrong, and still your vehicle has to work. That is what we do as a part of the DFMEA analysis, right? So now I'll not go in here. There's just a little part over there, but let's stop it here. I have not done a complete DFMEA analysis. I have not done a complete HARA analysis. So those are things which we would probably do it tomorrow, but I'll try to close the complete loop, right? So let me stop it at this point, and let me come back and say, like, ask if there are any questions. So okay, so let me just answer the questions one by one, and others, if you have any questions in the meanwhile, would be happy to answer. I think we have the last 10 minutes. I would probably reserve it for that. Okay, can you develop a systems engineering model for predicting failures? Yes, you can, right? So how would you do it? So all you'll have to do is, I mean, I say all you'll have to do, but it's not that simple in terms of the effort which is involved. So what you do is you first draw your architecture, right? So you have your motor, you have your MCU, motor control unit uh, is connected to your battery, right? I mean, when I say MCU, I say MCU plus inverter, right? I kind of talk about the integrated thing here. You have the battery, you have the BMS, right? So now you'll have to understand the motor control unit speaks its own CAN messages. BMS speaks its own CAN message. Now you'll need to have an instrument cluster. Instrument cluster will have its own requirements on how to display things. So then you will put a vehicle control unit here. So this speaks over CAN, this speaks over CAN, and then it speaks over CAN with this, right? So these are two-way communications which happens. So these would of course be the way it is connected. Now, how do you build a predictive system for it? You would have to go list out every single failure point. And for every single failure point, you would have to have a detection mechanism. Detection mechanism can be implemented in software, it can be implemented with hardware. You will have sensors. It can be a combination. Sometimes it will be not possible to detect it, in which case you just accept it for what it is and you try to work with it. Is it doable? Yes, it is doable. Is it easy? Um, Theoretically, this is all the logic there is, but practically speaking, it's another completely different thing. But yes, it is definitely doable. So just to kind of like make things interesting, let me just take the opportunity to kind of go and entire screen. Yep. Okay. So let me just show you a couple of work which I've been working on recently, right? So which should kind of give you an idea about how this whole DFMEA works. Um, right. So maybe first I should start with, so what we usually start with, right, is basically a document like this from the OEM, right? So they tell us, right? So they tell us these are the requirements which I have, right? So they say I'll need to have a steering angle sensor, I'll need to have a parking mode, a walk mode, right? They just give me these functions. So this is basically the inputs that sorry, this is the inputs that I get from the stakeholder, right? So the stakeholder is basically the OEM here. This is where I start. So then once I get this input, right? So this is what around 87 lines, right? Yeah, let's take it as 87 lines, not 87 exactly, but yeah, let's take 80 lines of requirements. So what I do from here is these requirements are, unfortunately, there is something. Okay, how do I drag to move? No, it's not moving. Okay, okay, hold on. Let me move this away. Okay, so now what I do is I take those requirements and I build it into my components, right? So what you see here, so these are the components list which I spoke to you about. I have the components. I mean, I'll have an ID and things for me to refer to. And from here, these are the calculations which we would probably be doing. So why do I have it here? Quick reference to understand what I'm doing. But the important thing here is I go to function realization, right? So the function which my customer gave me, I must map it to a hardware and I should see if the hardware is present, if I can realize it or not. I need to do this. And then I go to the most important parts, which is, yeah, this is my powertrain requirements, right? So the 84 functions which was given to me, that was basically the complete list of functions which was available. And from there, I had to break it down into what are all the requirements which I might have only for my powertrain. This is not for anything else, any other system, only for the powertrain. And only for the powertrain, if you look at it, I'm already at about 60 requirements for the powertrain alone, right? And if you go here, right? you will see this ASIL D, right? So these are the safety critical ones, right? So whatever is safety critical, I have the highest safety rating here. So let's go see what exactly is the safety rating here. It says the MCU shall accept torque request containing torque and blah, 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 100 milliseconds, which means every 100 millisecond it has to happen. Let's probably go to some other thing. It shall give a regenerative braking torque. The ramp rate shall not be exceeding 20 Newton meters per 100 milliseconds. Okay, let me probably hold on here. Why do I have this requirement? I'm talking about regenerative braking, right? But why do I say that it should not exceed 20 Newton meter in 100 seconds, 100 milliseconds? What is the reason? The primary reason is if I command the motor to do a lot of regenerative braking, there is a chance that the rear wheels might get locked up. If the rear wheel gets locked up, it's a safety critical thing, right? So I should basically be able to do it. And how am I executing it? Is the motor control unit capable of doing it? No. So the motor control unit is the executor of this particular function, but the host happens to be the VCU. And this also happens to be mapped out to a standard requirement. So the UNECE R136, like the EU homologation requirements, they will test it. So now once I have this, I can go back, I can see how they're going to test, I can go check if everything is right. So these are all the homologation requirements. When you get your vehicle, you can't just put it into the market, you'll need to get it homologated. Now, will everything be homologated? No, not everything might be, but some of it might be, some of it might not be. Anything which is QM is basically like a very low thing, right? So now it says that all the vehicles should be fitted with a 130/70 R17 rear tire, but is there a problem if it is not? I don't think so, right? I mean, it's not going to be a very big problem. I don't have to actively go and work around for it. So this is basically how we do it. I also have a very detailed HARA analysis, but let me probably work through that. Similarly, a requirement for energy systems, right? Drivetrain is what I've just managed to complete. So this is basically how we do. Um, is this designed? Yes, it is designed, but we call it as systems engineering. It goes one step on top of design, and but if you really think about it, the only things I'm doing here is I'm thinking about all the ways a failure can happen and how am I preventing the failure. That's basically all that I'm doing here, right? So I think it's a good point to stop here. Take just some more questions and we can probably start tomorrow. Requirements, yes, I will probably share. I cannot share the same thing. It's a customer requirement sheet, so I can't do that. I'll probably share whatever I can. I'll probably share it tomorrow, right? Um, so, yep. Thanks a lot for joining in. I'll try to bring in some more interesting case studies. And if you find it interesting, then I'll also sit and let's try to do a complete decomposition and a safety analysis. Let's try to do it live, and we can probably do that. I'll share the entire thing, right? I'll share the entire thing with you. I'll tomorrow we will take a requirement, we will break it down, we will understand what are the homologation requirements, where to get it, how to map it, and we'll probably by the end of the session, we'll try to like have it completely mapped out, right? So thanks a lot for joining in. Have a
Yeah.
nice evening, and I'll meet you again tomorrow.